Elon Musk wants 1 million people on Mars by 2050. NASA is planning crewed missions for the 2030s. SpaceX's Starship, the most powerful rocket ever built, is being designed with one destination in mind. And almost everyone talking about this is skipping the part that should stop everything. Mars has a flaw, not an engineering problem we can solve with better technology, not a funding problem we can fix with more money. A fundamental physical flaw baked into the planet itself that no amount of human ingenuity has yet answered. And when Derek from Veritasium looked at the actual numbers, he called it one of the most underappreciated facts in the entire conversation about space colonization. By the end of this video, you'll understand exactly why, and you will never look at Mars the same way again. Stay with us until then, and don't forget to subscribe to the channel. Before we get to the fatal flaw, let's be fair to Mars, because on paper, it is genuinely the best option we have. It is close, at its nearest, about 54 million kilometers from Earth. It has a day almost identical to ours, 24 hours and 37 minutes. It has water frozen beneath the surface and at the poles. It has carbon dioxide, which can theoretically be converted to oxygen. It has soil containing the chemical elements needed to grow food. Surface temperatures, while extreme, are not as severe as deep space. In some equatorial regions on a summer day, they can reach 20 degrees Celsius. Compared to every other option, Venus, the Moon, the asteroid belt, Mars is the closest thing to achievable. And the dream is real. A second home for humanity, a backup civilization, a place where the species continues even if Earth fails. It is a beautiful vision, and the people building toward it are serious, brilliant, motivated, but there is something sitting at the center of that dream. A problem so fundamental that even the most optimistic Mars scientists struggle to explain how it gets solved. It is not the cold, not the thin air, not the distance, not the cost. It is something invisible, something you cannot build a wall against, something that is hitting the surface of Mars right now as you watch this video, and has been for billions of years. Mars has no global magnetic field. On Earth, our magnetic field is generated by the movement of liquid iron in our planet's outer core. It surrounds the entire planet like an invisible shield, deflecting the constant stream of charged particles flowing from the sun and from distant stars and supernovae. Without it, those particles hit the surface directly, stripping away the atmosphere, bombarding everything, living, non-living, everything. Mars had a magnetic field once. About 4 billion years ago, its core cooled and solidified. The magnetic field died, and without it, the solar wind began stripping Mars's atmosphere away. Over billions of years, the atmosphere thinned to almost nothing, and the radiation began hitting the surface directly. Today, the radiation dose on the surface of Mars is approximately 700 millisieverts per year. On Earth, the average person receives about 3 millisieverts per year. That means standing on Mars, you are receiving roughly 230 times the radiation of a person on Earth every single day, every single year, permanently. To put that in medical terms, the safe annual radiation limit for nuclear power plant workers on Earth is 50 millisieverts. Mars gives you that in less than 4 weeks, and that is the baseline, the normal, calm, no solar storm number. When the sun decides to erupt, it gets dramatically worse. In August 1972, between Apollo 16 and Apollo 17, the sun released one of the largest solar particle events ever recorded. If an astronaut had been on the moon at that moment, outside a spacecraft, in a standard spacesuit, the radiation dose received would have been lethal. The Apollo astronauts survived only because of timing, pure luck. Nobody was outside when it happened. Now consider this on Mars. Solar storms cannot be predicted more than a few hours in advance. They release enormous bursts of high-energy protons that travel at a significant fraction of the speed of light. They arrive fast, with little warning. On Earth, a solar storm produces beautiful auroras. On Mars, with no magnetic field, it produces a radiation spike that can reach several times the already deadly baseline dose in a matter of hours. So you're living on Mars, it's a Tuesday. The sun releases a massive coronal mass ejection. You have maybe 30 minutes warning. You need to be inside a radiation shelter immediately. Every single time for the rest of your life on Mars, with no way to predict when the next one is coming. And your shelter, whatever you've built, needs to absorb that radiation completely. Because even a partial exposure, repeated over years, accumulates into cancer, into neurological damage, into organ failure. This is not a theoretical future problem. This is the condition on Mars right now, and every proposed solution has a critical flaw of its own. Engineers are not ignoring this. They have proposed several approaches, and each one reveals just how hard the problem truly is. Solution 1. Underground habitats. Live in lava tubes, ancient underground tunnels created by volcanic activity. Meters of rock above you absorb the radiation. It works, in theory. But it means living underground, permanently. No windows, no outdoor space, no sunlight for years, possibly decades. And the psychological consequences of that are themselves a serious threat to human survival. Solution 2. Regolith shielding. Cover your habitat with several meters of Martian soil. The soil absorbs radiation. Again, it works partially, but Martian regolith is toxic. It contains perchlorates, highly reactive chemicals that are poisonous to humans and destructive to electronics. The same soil protecting you from radiation is a health hazard if any of it gets inside. Solution 3. Water walls. Line your habitat walls with water. Water is one of the best radiation absorbers known. Effective, but enormously heavy to transport from Earth. And extracting enough water on Mars to build walls out of it is an engineering challenge that remains unsolved. Solution 4. Electromagnetic shielding. Generate an artificial magnetic field around the habitat, like a miniature version of Earth's magnetosphere. The power requirements are staggering. The technology does not exist at the scale needed. Every solution either requires technology we don't have, resources we can't easily access, or creates a new problem as serious as the one it solves. But radiation is only the first flaw, because the second one is something that cannot be shielded against at all. Mars has 38% of Earth's gravity. That sounds like a minor inconvenience, maybe even an advantage. Things weigh less, moving around is easier. But here is what 38% gravity does to the human body over time. We know what zero gravity does to astronauts on the International Space Station. After 6 months in microgravity, astronauts return to Earth with significant bone density loss, muscle atrophy, vision problems caused by fluid shifting toward the brain, heart changes, immune system suppression, and that is zero gravity. The extreme end. Scientists don't know what 38% gravity does long term, because no human has ever experienced it long term. We have never had a research station on Mars. We've never kept animals in 38% gravity for extended periods. The honest scientific answer is, we do not know. Will 38% gravity prevent bone loss? Partially, completely, not at all. Will children born on Mars develop normally? Will their bones form correctly? Will their cardiovascular systems develop the same way as Earth children? Will they be able to return to Earth? Or will Earth's gravity be too strong for bodies that grew up in 38%? These questions have no answers yet, and here is the disturbing implication: the only way to get those answers is to actually send people to Mars and observe what happens, to use human beings as the experiment. And if the answer turns out to be that 38% gravity causes permanent physiological damage over years, we discover that only after people are already living there. 225 million kilometers from the nearest hospital. Let's say we solve the surface problems, the radiation shielding, the gravity question, the food, the water, the air. You still have to get there. The journey to Mars, using current propulsion technology, takes between 6 and 9 months. During those 6 to 9 months, you are in deep space. No magnetic field, no atmosphere. Just a thin metal hull between you and the full force of cosmic radiation. The radiation dose during transit alone, in each direction, is estimated at around 300 millisieverts. Round trip, before you've even lived a single day on Mars, you've already absorbed 600 millisieverts, more than 10 times the annual safe limit for radiation workers on Earth. And during those months in microgravity, your bones are already losing density, your muscles are already atrophying, your vision is already beginning to change. You arrive on Mars after 9 months of physical deterioration, and then you have to function, build, survive in an environment that is actively trying to kill you, in a body that is already weakened by the journey. And the moment things go wrong, and on a frontier this extreme, things will go wrong, the nearest help is a communication delay of 4 to 24 minutes, one way. So a back and forth conversation with Earth takes up to 48 minutes. No real-time guidance, no emergency evacuation. You are on your own, completely, permanently. There is one more problem that almost never makes the headlines, but scientists who study Mars habitability consider it one of the most serious long-term threats to human settlers: the dust. Mars is covered in fine, dry, chemically reactive dust called regolith. Unlike Earth's soil, which has been weathered over billions of years by water, wind, and biological processes, Martian regolith has never been weathered. Its particles are sharp, angular, jagged at the microscopic level, and it gets into everything. Mars experiences global dust storms, storms so large they can cover the entire planet for weeks at a time. In 2018, a global dust storm lasted for months and killed NASA's Opportunity rover by blocking its solar panels completely. That dust, if inhaled by humans, behaves like asbestos in the lungs, sharp particles embedding in lung tissue, causing progressive irreversible damage, a disease called silicosis, but in Martian form. And the dust also contains perchlorates, toxic chemicals that disrupt thyroid function, damage the immune system, and are corrosive to electronic equipment. Every time an airlock is opened, every time someone comes in from outside, that dust comes with them, and over years it accumulates inside the habitat, inside the air filtration systems, inside the lungs of everyone living there. No current filtration technology has been proven to handle Martian dust indefinitely at scale without failure. Here is what Derek from Veritasium has argued, and what many Mars scientists privately agree with when the cameras aren't rolling. The question is not whether humans can reach Mars. SpaceX will likely get people there within a decade. The engineering of getting there is being solved. The question is whether humans can stay, whether a self-sustaining colony, one that doesn't need constant resupply from Earth, is physically possible given the radiation, the gravity, the dust, and the complete absence of a solution to any of these that has actually been tested at scale. And the most honest scientific answer right now is we don't know. Not it's very hard, not it'll take time. We genuinely do not know if long-term human habitation on Mars is biologically compatible with the human body as it currently exists. And that uncertainty, before we send the first settlers, is the conversation the public is not being invited to have. Because the plan, as it stands, is to send people to Mars and find out when they get there Use the first generation of Martian settlers as the dataset. That is not a criticism of the mission. All great exploration has involved risk. The first people to cross an ocean faced similar unknowns, but they could turn around. They could come home. The first people on Mars cannot. Mars is not a trap. It is a frontier. And every frontier in human history has demanded that the first people who crossed it accepted risks that the people who came after them did not have to face. The fatal flaw in Mars is real. The radiation is real. The gravity question is real. The dust is real. The isolation is real. And no, there is no complete solution to any of them yet. But here is the other truth. 50 years ago, there was no solution to landing on the moon. 40 years ago, there was no solution to building a permanent space station. 10 years ago, rockets could not reliably land themselves back on Earth. Now they do it routinely. The history of space exploration is a history of people staring at problems that had no solution and building the solution anyway. The fatal flaw is real. The question is whether the generation alive right now is the one that solves it, or whether the first people on Mars will be the experiment that tells us if it's even possible. Now, there is one proposed solution to Mars' radiation problem that sounds completely insane, but that serious physicists have published papers about. A solution that involves not shielding Mars, but giving it back its magnetic field, artificially, using technology we are beginning to develop right now. Whether that is genius or science fiction is next.